These are research presentations. They go a little bit more into the technical detail than what you have heard before. However, the two presenters will try also to convey on the high level what they're trying to do. So even if you're not an expert in that particular field, you should get some benefit from these presentations. The first presentation is given by Professor Roberto Guanciale. And why don't you start?
Okay, thank you. So this presentation is on one part of Provable security. We use formal verification and formal model to analyze security of system and to rule out some of the bugs that we have seen this morning. And a fundamental component of formal verification are models. So models allow us model of system, model of software, model of the hardware where your software is running. And these models are usually used, first of all, to understand the behavior of the system so that we can prove and predict property. And then also somehow to confine and describe against which kind of attacks we want to verify properties of our system. So in this talk, I will focus on proving properties of proving confidentiality property, in particular proving resilience against a side channel attack. And I will mainly discuss about, what is a side channel, what are the models that we use to describe this side channel and prove properties to prove resilience against this type of attacks, why the model that we used until 5 years ago were basically broken, and what we are doing to repair these models, since if the models are wrong, the properties that we are proving are basically incorrect. So there are many types of side channel, power consumption. Later we will see electromagnetic radiation and power consumption attack, sound, temperature. I will focus on timing channel. So what is a side channel attack? Well, basically the idea that an attacker can learn some information about the system by measuring some properties of its execution. Like this is a typical example of an ATM code that checks the PIN code of your card. You have a while loop that checks basically every individual PIN if the PIN is equivalent to the code that is the PIN of your card. And this system returns as soon as the PIN is wrong. So an attacker may monitor how long it takes for this code to execute. If this code is fast, it means that the first digit was wrong. If this code is run in a longer amount of time, it means maybe that the second PIN code, the second digit was wrong, and so on and so forth. So in this way, an attacker basically can reduce the complexity of a brute force attack by identifying, by submitting a random PIN and measuring the execution time of the ATM and using this to learn basically which digit was wrong. So I will focus actually on another type of attack that are side channel attacks that rely on specific optimization of CPU architecture, in particular the usage of cache. So we have today really fast processors that are really fast to execute computation, but they have to deal with a relatively slow memory. And to improve performance of this system, usually we use cache, right? A really small memory that sits between the processor and the actual memory that can cache some information that can be used faster from the processor. Usually this cache is much smaller than the memory. Like for instance, in this example, we have a cache that is just 4 kilobytes, a memory that is much larger, maybe 8 gigabytes. And the idea is that this cache is split in small blocks. In this example, I just have a block of 64 bytes. And basically, this block of memory will be loaded automatically inside the cache whenever the processor needs this information. Now, since the cache is much smaller than the memory, we usually have collision. That means different regions of memory will have to sit on the same region of cache. And this is the main source of a side channel, right? Because if this dependency on the fact that the same region of memory can go in the same cache, it means that I will not be able to access, for example, at the same time the memory at address 0 and the memory at address 4 kilobytes because they sit on the same region, right? And this will lead to different execution time of my software that can be used by an attacker to learn information about my software. Right? So the point is that these caches are basically transparent. We don't really have to program them. It's the architecture that automatically fetch things from the memory, load this into the cache. And they are basically shared. Many times we have two different programs that are running on the same system, and they may share cache, basically, and may pollute cache. One software can pollute the cache that is used by another software. As I said before, there are collisions. That is the main source of information leakage. And cache misses require more time because, well, if I read something from the memory and this is not into the cache, the processor will have to read things from the cache and from the memory, store this into the cache, and this memory access will be slower. By looking at this, how long these memory access take, the attacker can learn information about my program. So, why cache attacks are dangerous? Well, first of all, as been demonstrated, they can actually be used to compromise security of cryptographic system. For instance, if you use a non-secure RSA implementation, an attacker can measure how long it takes to your software to answer a wrong login request and use this time to learn an RSA key to a remote SSH connection. These are also quite difficult to audit, right? So the attacker just measures basically how long it takes to your software to execute and doesn't really leave any trace in the system. So if you have a side channel in your system that can be exploited by an attacker, well, there is no trace left in the system. And once you identify that your program was vulnerable, you basically need to assume that all information has been leaked, and you need to revoke, for example, all cryptographic key and redistribute the key, and so on and so forth, right? So the security condition here usually is the execution of two states that should be indistinguishable for the attacker should have the same footprint on the channel, right? So for instance, if I have a remote login that depends on a cryptographic key, the time needed for this remote login to answer an attacker should be independent on the content of the cryptographic key. Okay, and that's the example of before. So this code is not secure because the time needed to answer to a request depends on the actual password here, on what is the first digit that differ from the password, and is not executed in constant time. So to be safe, this program should have, to be secure, this program, we should have that two states should have the same, that have the same PIN but different password, will execute in the same amount of time. Now, to verify this property, we need the model of side channel. And usually it's hard to have a precise deterministic model of these channels for many reasons. So in the case of computer architecture, these are just too complex. Like a modern processor consists of billions of transistors. They have many optimization inside. And when we analyze software, we don't want to take into account all this complexity. There are also many undocumented features. For example, there are different cache replacement policy, different layout of cache, different hierarchy of cache, and so on and so forth. Some of these features may even be closed source. Like in the case of Intel, Intel doesn't disclose the replacement policy. And in any case, Intel will never allow you to look into the processor and see the processor design. Also, we have different processors that implement the same instruction set architecture. For example, in the case of ARM, we have one single instruction set architecture, and then we have many different processors that may have complete different side channels. Okay? So we need some models that abstract from the actual detail of the processor and the cache, but still allow us to verify resilience against a side channel attack. And these model users are called observational models. So the idea is that we take the instruction set architecture, so we take basically the behavior of the processor, and we extend this instruction set architecture with a leakage function, something that says for each instruction what this instruction may leak about the execution of the software. For instance, if you are after leakage due to data cache, that are the case that I discussed before, since accessing the memory in different locations may affect different line of the cache and different content of the memory be loaded into the cache, an observational model may say that, well, this program that performs a comparison here and execute this branch in one case and the other branch in this case, may leak at this point the content of the register X3, because at this point the program is reading from the location X3. And this location will affect different line of the cache. Okay? Notice that this observational model basically doesn't say anything about how the cache is designed, how big is the cache, how is designed the processor, and so on and so forth. It somehow over-approximate, this leakage function over-approximate what can be leaked by our software, right? And then the goal, the security condition now become that the execution from two states of our software should be indistinguishable for the attacker, then should have exactly the same sequence of observation, right? If the leakage function answers exactly the same result, it means basically that we are leaking the same, well, we affect the side channel with the same kind of information, and since these are information that are already public, already known by the attacker, well, this information cannot be exploited by the attacker to learn anything about the system. Right? So again, in this example here, that means that this program is secure only if at this point the content of the register X3 is not depending on any secret information, basically, right? So if the content of the register X3 at this point contains, for example, a cryptographic key, then this program will be considered non-secure. Now, our goal here is to do validation of this model. Since we rely on this model to verify security of the software, we need to be sure that if two programs are what we call observational equivalent, that means the program generates the same sequence of observation, then indeed, when we run this program on the real hardware, well, the attacker will not be able to distinguish basically two executions, and these two executions will have exactly the same footprint on the channel. And well, are the existing model unsound? Is this something we need actually to check? Well, yes, because 3 years ago, actually 4 years ago, has been shown that all the models that we have used to do this kind of analysis were wrong. Mainly because we have overlooked one specific feature of processor, that is speculative execution. Now, processor, to speed up execution, sometimes may execute instructions that are not supposed to be executed, but are executed speculatively by the processor, and then later on the processor may roll back the effect of this instruction if this instruction were not needed. Unfortunately, the processor can only roll back this effect on the processor itself, and cannot roll back the effect that this instruction had on the cache. So this instruction can still leak information through the cache. And this is the standard example. So here we have a program that performs a comparison. This register X1 is a parameter sent by an attacker. We check if this register is less than the size of an array A. So this is the array that we have here. We suppose that this array is public. There is nothing secret inside this array. So if this index is greater than A, then we return. That means we avoid basically a buffer overread. Otherwise, we read inside the array in the position X1. So we should read inside this public content. And then we use this array to read an index that is used to read into another array, that is the array B, that is also public. So this program should be OK. And accordingly to the standard observational model, this program will leak the content of the register X1 that is controlled by the attacker. So there is nothing secret there. Since here is reading in the array A indexed by X1, again we leak this index that again is public, and then here we leak the result of this load that is the content of the array A that again is public, so there is no problem. Unfortunately, a processor can execute this instruction in speculation. That means even if the input of the attacker is larger than the size of the array, the program may still execute this instruction in speculation, may have a buffer overread, read outside the array A here, read, for example, in a complete different area of memory where we have a cryptographic key. So read this cryptographic key inside the register X2, and then use this register X2 in this load, and then perform a secret-dependent memory load that will leak the content of the key. Okay? So this is called a Spectre attack. So how do we check if our models are correct and how we repair the model. Well, we have developed a new tool that is called ScanV that validates this model via testing. So the idea is that we generate a program, then we generate some random input for this program, and then we check if this input leaks some information on an actual processor. Now, differently than standard functional testing, where you need to generate only one input, right? Well, you need to generate many inputs, but every test uses just one input. Since here we are after information leakage, we need to generate two inputs, right? And check if these two inputs have some difference basically on the side channel. And these two inputs basically should be indistinguishable according to the observational model, and that means basically should have the same footprint on the cache. So this is the pipeline of this tool. So first, we take the program, and we lift this program to a new intermediate language that we call BIR, that is used basically to develop in a tool in a way that is independent of the computer architecture. So for example, we can take ARM, x86, and so on and so forth, and transform this to this intermediate language. Then we add the observation to this intermediate language. For instance, if we say that at this point, the observational model expects that we leak this address, at this point, we'll add an observation here of the register X3. Then we use a symbolic execution to try to understand what are the possible observations of this program. In this case, we will see that in one case where the register, the two values of this register are different, we take this branch, there will be no observation. In the other case, the symbolic execution will tell us that we will have one observation that is equivalent to the value of the final value of the register X3 that is equal to the sum of the register X4 and X3. That's according to this program. Then we need to generate a relation that tells us which states have the same observation. Well, once we have symbolic execution, we use basically self-composition to say that, well, if the first state takes the branch and the second state takes the branch, then these two states are equivalent if they both take the branch and have the sum of these two registers to be the same. And if the first state doesn't take the branch and also the second state doesn't take the branch, then it doesn't matter the content of the register since they do not perform any memory load. Then we use an SMT solver with this relation to generate this input test. And finally, we run this on a physical processor. In our case, we use Raspberry Pi 3. So we have a really small bootloader that loads the program, set up the environment, set up the first state, execute the program, check the cache, clean everything, load the second state, execute the program, and check the final state. This is executed bare to metal under the operating system. That means there is no noise. So this is the worst case scenario, basically, for a defender. And what do we get? Well, that ARM claimed that Raspberry Pi 3 is immune to Spectre, and this is not true. So we have identified, by running 16,000 tests, around 3,900 different counterexamples. So while ARM claimed that the processor is not affected by speculative leakage, well, it's not affected by the original version of Spectre, that is the example I presented before, but is affected by different type of speculative leakage. Basically, it can leak just the first memory load. So it's a slightly different. So in this case, for example, the processor may leak the content of the register X3, even if these two registers are different, basically. And this is a problem because, well, we cannot fix processor, right? It's quite expensive to fix processor. So in this case, we need to fix the observational model. That means the observational model needs to take into account that this processor may leak something more than what has been promised by the vendor. So some concluding remarks. So existing observational models are often overlook some information flows, and this is a problem for verification because, well, if we verify against the wrong model, we verify wrong properties. And so without sound model, we cannot reason about software security. And this approach using observational equivalence provides a good strategy to drive tests because we have seen that, well, we can identify problems in actual processors, even if the vendor claimed that these processors were secure. So what are the new challenges now? Well, one direction is how do we repair the model? Now we got all these counterexamples here, And it's really tedious for a developer, well, for a verifier, in my case, like me or a PhD or a postdoc, right, to take the model and say, how do we repair the model? Which are the missing observations of this model, right? So one interesting direction is, can we take this counterexample and try to learn automatically what is leaked by the processor so that we get a sound model for that processor, basically. Another challenge is, well, for now we use this validation using hardware as a black box. So we don't look into the hardware in the case of ARM because we don't have the design of the processor. But in the case that you have an open source processor, for example, in the case of RISC-V, can we drive the test using the hardware design so that we can have some guarantee that we have covered all possible behavior of the hardware and all possible peculiarity of that specific processor? That's all.